All right, so this problem says a man stands on a merry-go-round that is rotating at 2.5 radians per second. If the coefficient of static friction between the man's shoes and the merry-go-round, mu s, is 0.5, how far from the axis of rotation can he stand without sliding? Okay, so let's say the man is standing there at a distance r. V is his velocity. Okay, and if it's not, okay, the static friction force is providing the centripetal force. Okay, and well, if let's say he's standing at the maximum distance, so we have the maximum static friction force acting. Okay.
What
Now,
does mu stand for?
Mu.
Oh, is that what that is? U is the mu.
This is mu.
Right in the diagram.
No, V. That's his velocity. All right. So this is the top view of the situation. Let me do a side view. So here is the side view, and here is the man standing. Here is the static friction force that's providing mg. Here's the normal force. Okay, so Fs max is mu s times F normal equal to mu s times mg, and this should equal, so this is Fs max, and we want Fs max equal to centripetal force mu s mg is equal to centripetal force is mass v square by r, or since I've written small r. And so here's an interesting thing. The mass cancels. What that means is no matter who's standing there, if they're wearing the same shoes or the same type of soles, okay, they'll all slip at the same time, so to speak. Yeah. All right, so this is the maximum velocity it can go at before you'll slip. You know? So what is it that, how far from the axis of rotation that can he stand? Oh no, that's velocity is that. Okay. No, the velocity is given, sorry. So velocity is given, and you can see this as r increases, mu s is smaller and smaller. So wait a second. You're given the static coefficient of friction. Yeah, okay. Right. So mu s, okay, mu s is given. That's the maximum static friction force. Now you can think of static friction force, if this is smaller, mu s would be smaller. Okay. Smaller this is, bigger r would have to be for a given speed. Okay. So you have to stand further out not to slip. If it was a frictionless surface, you would have to, of course, stand at infinity. Okay? You can't go in a circle if it was a frictionless surface. Okay? So, how would we say? Okay, so this would be R minimum, the smallest R you can stand at. If you stand any closer than that, you would slip. If you stand any closer than this number would be bigger, and this is not up to it to prevent you from slipping. Yep.
So you're saying that for a given speed, it's telling you how close you would have to stand to the center?
You have to stand further from this point.
So how far you would have to stand from the center?
That's the smallest distance you can stand from the center.
Okay.
Okay, so it's harder to stand closer.
And it's going that given speed.
Yep. And you guys see this in when you're driving a car. The sharper the curve, the harder it is to do. To make a sharper and sharper turn, you need stickier and stickier tires. Okay, so what we're saying is, smaller this is, bigger this has to be. Okay. All right. So R min is V square by mu SG. All right. So we have to find V. V is R omega. So that comes in there again. R min equal to R min square omega square divided by mu SG. Okay. I put in that variable too soon, but anyway, that is the smallest. You have to stand at least that far away not to slip. If you're any closer than that, you will slip. Okay. All right, so let's put these numbers in. Mu s is 0.5, g is 9.8 meters per second square. Okay. And so this works out to okay, so let's draw a circle. So this is the slip zone. And non-slip zone. Okay. For omega equal to 2.5 radians per second. Okay, so let me ask you. So if you rotate it faster, what will happen to the slip zone? Huh? It so if this omega increases, R decreases. The slip zone shrinks. And that makes sense. As this goes to infinity, you would have to, the only place you can stand is the slip zone shrinks to 0. You'd have to stand on the axis not to slip. Okay? Yep. Yes, go.
Well, first, can you flip back to the other?
All right.
So, as you go further from the center, doesn't it move faster relative to, like, a point further to the end is moving faster?
Okay.
The question says how far away can you stand?
All right. So let me add a page. So here's Kyle's question, which is probably what throwing you guys off. So here's what I should have done. Okay. So the centripetal force is okay. The static friction force is providing the centripetal force. Mu s mg equal to m v square by r, and we're going to express v in terms of omega. So v is r omega. So mu s mg equal to m r square omega square divided by r. One of the r cancels, okay, the m cancels. Mu s g equal to r omega square. So here, this equation will answer your question. If you keep omega constant, greater r is, the further you are, the greater mu s has to be. The stickier your shoes has to be. Okay?
So basically, if you're maintaining speed, if you're driving at 70 miles an hour, how tight of a turn can you make? It's not saying how fast it's rotating. It's saying how fast you are actually moving.
Mm-hmm.
So you're saying, so the further we are away, the stickier shoes have to be?
Right.
So wouldn't that mean that the slip zone would be
Okay.
further apart? That'd be great.
Okay, let's let me make sure I are okay, the coefficient of static. Yeah, so this thing is implying, okay, so
It's all about the relationship between your speed versus how fast you rotate.
no, Kyle is right, and so I got this backwards. This is the way to point out, see, so the further away you're going, the stickier shoes you need for a given angular speed. So given this, there's a maximum distance you can be before you start slipping. So I got this backwards. So he's right. So this is the non-slip zone, and this is the slip zone.
That would make the R minimum R maximum, right?
Yeah, so that would, okay, so we'll call that R max. And you see that sort of, I guess had we read this carefully, how far from the axis of rotation can he stand without slipping? So that's the maximum distance he can stand. And beyond that, he'd slip. Yep, yep, you were right. Okay, you guys understand? So I guess you do have to think about it a bit. It threw me off the loop too. I slipped. I was standing beyond the circle.